This is A. Srinivas, lecturer in physics, Vignan Junior College, Vadalmudi. Students, today in this part of our discussion, I would like to explain objective revision in potential. We know that capacitance and potential is a very important chapter in objective point of view in JEE Main and eamcet. In it, we now in this part of our discussion, we revise the equations belongs to potential. Here the contents that we discuss. First one is electrical potential and potential difference concepts, and second one electrical potential due to single point charge, and third one electrical potential due to group of charges, and electrical potential due to an electric dipole. First four belongs to the potential. Potential due to point charge and potential difference concept, potential due to single point charge, potential due to group of charges, and potential due to electric dipole, and then followed by equipotential surfaces. With the help of that, we derive the relations between the potential and electric field, force and potential energy in case of uniform electric field and non-uniform electric field, and finally expressions for electrostatic potential energy. Here the first one is electrical potential. Suppose we have charge Q at a particular point. So let us consider charge Q. Let Q be any arbitrary charge. Let Q be any arbitrary charge kept at point O. Let this be a point positive charge kept at point O at rest, stationary point charge. Then work required to bring unit positive charge from infinity to this any arbitrary point R. Suppose at a distance R, we would like to know the potential V. Let V be the potential at some point P, which is at a distance R. That is numerically equal to work required to bring unit positive charge from infinity to this point, and that is calculated by the formula minus integral E bar dot dr bar, because electric field due to this charge is away from positive charge and we are bringing the positive unit charge towards it. Displacement and force or electric field are in opposite direction, hence we are using negative sign. Use E is equal to 1 by 4 pi epsilon naught Q by R square dot dr. So in this derivation we find potential is equal to 1 by 4 pi epsilon naught Q by R. So potential due to point charge at some point P at a distance R from Q is ultimately given by V is equal to work done in bringing unit positive charge is equal to 1 by 4 pi epsilon naught Q divided by R. And then potential difference. Suppose consider charge is bringing from infinity to point P. Let us consider the AB one point here, BB another point. Potential at point A is VA and potential at point B is VB. Then work required to move the charge from A to B. Work required to bring unit positive charge from A to B is equal to potential difference between those 2 points. So final potential is VB. Initial potential is A, so potential difference is VB minus VA. That is equal to potential value difference at point B and at point A. That is also equal to work done in bringing unit positive charge from A to B. In expression form, we write the potential difference between points A and B is also equal to Q by 4 pi epsilon naught, because it is equal to VB minus VA. Just we subtract VA potential from VB potential, Q by 4 pi epsilon naught into 1 by RB minus 1 by RA. RB is the distance at B from O, RA is the distance of A from O, then potential difference is given by this formula. So here in this slide we write the expressions of potential and potential difference. Next, go for the next concept. Here in this concept we would like to know electrical potential due to group of point charges. Here in this diagram, let consider different charges. Let Q1 be the charge at a particular point, and Q2 is the second charge, Q3 is the third charge, and so on. Q4 is the fourth charge, Qn is the nth charge. In this region we have Q1, Q2, Q3, Q4 and so on. Qn are the n charges kept in this region, and we would like to find out potential at point P, and we assume potential at point P, at P the work required to bring unit positive charge from infinite to point P is the potential due to all charges, which is equal to sum of the potentials due to each charges. Potential is a scalar quantity, therefore net potential is the algebraic sum of potentials. Due to positive charge, the expression for potential is in positive value. Due to negative charge, expression for potential is in negative value. Then algebraic sum of potentials due to all charges at given point P is the net potential at point P due to this group of charges. Suppose this point P is at a distance r1 from Q1, and it is at a distance r2 from Q2, at a distance r3 from Q3, and Q4 is at a distance r4 from P, and Qn at a distance Rn from P. Then the potential due to all the charges is given by the net electrostatic potential at point P is simply equal to algebraic sum of potentials of individual charges at that point. So potential at point P is equal to algebraic sum of potential due to all the charges at that point V1 plus V2 plus V3 plus and so on Vn. This is the expression, and from this we get total potential is equal to, here V is equal to 1 by 4 pi epsilon naught sigma I is equal to 1 to n Qi Ri. So here we can write this one as simply 1 by 4 pi epsilon naught. V1 means Q1 by R1, as Q2 is at R2 distance, Q2 by R2 and so on. Vn, Qn is at R distance, Qn by Rn. So this is simplified as sigma I is equal to 1 to n Qi Ri. This is the way of finding potential due to group of charges. Here next one, the potential due to dipole. Students, so far we discussed about potential due to point charge, potential difference and potential due to group of charges, which is algebraic sum of potential due to all the charges at the given point. Next, the idea is potential due to dipole. Students, so we know that dipole consisting of two equal unlike charges kept at some distance of separation. Let minus q be a charge kept at this point, and plus q is the charge kept at another point, and these two are separated by some distance. This pair of equal and unlike charges constitute a dipole, and we know that dipole moment is P. The dipole moment of the given dipole is P, which is the product of charge, magnitude of one charge and distance between the charges. If d is the distance between the charges, q into d is dipole moment, which is directed from negative to positive charge. Here we would like to find out potential due to this dipole at some point P. Potential due to this dipole at some point P, that from midpoint draw a line to the point P. A line drawn from midpoint of the dipole to the point P makes theta angle here. So in that situation, what is the potential at point P due to the dipole means as we discussed. Now, potential at any point due to group of charges is the algebraic sum of potentials. Therefore, here from plus q, the distance is r1. So, distance from plus q is r1. That r1 is equal to, if this distance drawn from midpoint to the p, let O be the midpoint, distance drawn from midpoint to p is r, then distance from plus q to p is r1, that is equal to r minus r cos theta, as well as distance from minus q is r plus r cos theta, so r2 is r plus r cos theta. Then potential at point P due to both the charges is V1 plus V2. V1 is the potential due to positive charge, V2 is the potential due to negative charge. Net potential is V1 plus V2. By using that, V1 is equal to 1 by 4 pi epsilon naught q by r minus r cos theta, and V2 is equal to 1 by 4 pi epsilon naught q by r plus r cos theta, and simplify the equation. Ultimately, we get potential due to dipole at point P, which makes theta angle with dipole axis, is 1 by 4 pi epsilon naught p cos theta by r square. Remember this formula to solve. In recent years also, some questions were given in JEE Main as well as eamcet exams in dipole, potential due to dipole concept. So to answer those questions, this is enough. Potential due to dipole is V is equal to 1 by 4 pi epsilon naught p cos theta by r square. Here P is the dipole moment, that is q into distance between the charges. Theta is the angle made by the point with dipole axis, and r is the distance of P from midpoint of the dipole. Now comes to subcases of this formula. On axial line of the dipole, on axial line, if you consider this point P on axial line, then theta reduces to 0 degrees. When you consider axial line point, theta becomes 0 degrees, then cos 0 is 1 in the above formula. Therefore, 1 by 4 pi epsilon naught p by r square, dipole moment by r square, is the potential due to dipole on axial line. Whereas for equatorial line, if you consider the equatorial line, here equatorial line is like this, a perpendicular line is the equatorial line, that makes 90 degrees angle with dipole axis. Now theta increases to 90, replace theta is equal to 90, cos 90 is 0, so potential is 0. So due to dipole, potential at any point on equatorial line, due to dipole, potential at any point on equatorial line is 0. Already we know that due to this dipole, electric field on equatorial line is not 0. It is 1 by 4 pi epsilon naught p by r cube. 1 by 4 pi epsilon naught p by r cube is the electric field intensity due to dipole on equatorial line. Hence we have a condition. We can answer some questions like, is there any point which having 0 potential and non-zero electric field? Yes. Any point on equatorial line of dipole, electric field is non-zero, given by 1 by 4 pi epsilon naught p by r cube, whereas potential at any point on equatorial line of dipole is 0. This is a special case. Now go for the next case, equipotential surfaces. It is the locus of all points which having same potential. Locus of all points that having same potential is known as the equipotential surfaces. So potential is same, all points of the surface, such surfaces are known as the equipotential surfaces. Here, for a uniform electric field, let us consider some examples to know about the equipotential surfaces. So let us consider equipotential surface exists in uniform electric field. So once again, dear students, see the animation. I am showing the uniform electric field by the parallel equal spaced lines, that is the notation of uniform electric field, and perpendicular to them I draw some planes which are showing equipotential surface. Once again, looking at the animation, yellow color lines indicates the uniform electric field. Here E bar is uniform electric field, pictorially indicated by the yellow lines, which are equally spaced parallel lines directed in same direction, shows the uniform electric field. Here this is let it be one plane surface taken perpendicular to the uniform electric field. Itself is equipotential surfaces. Potential is same at each and every point on the surface. Hence this region 1 is one equipotential surface. As well as if you consider the second one, it also having the same potential, because to bring unit charge from infinity to this any point of the surface. Suppose if you consider the second plane drawn perpendicular to the uniform electric field, then work required to bring unit charge from infinite to any point on this plane is same. Hence potential is also same for all points of the surface. So this surface is considered as equipotential surfaces. Similarly, like that, if we draw any number of plane surfaces perpendicular to the electric field, each and every plane surface becomes an equipotential surfaces. This is the way to draw equipotential surface in case of uniform electric field. Here, the potential at all points on the surface is considered by V1, and potential on all points of the surface is V2. Potential on all points of the surface is considered by V3. Here, these are said to be plane equipotential surfaces. As we represented here, they are plane equipotential surfaces. Here, next example, to know about the equipotential surfaces, let us consider an isolated point charge. Isolated stationary point charge is located in a region. Let this red dot indicates isolated positive charge kept stationary in a region. Here, from this isolated charge, the electric fields are directed radially outward in all directions. The electric field lines are directed radially outward as shown here. And if you consider any concentric sphere, we can draw any number of concentric spheres of different radii around this positive charge by considering positive charge as center of the sphere. So let us draw those concentric spheres. See, once again students, here now let us have only we have the field lines which are radially outward from a stationary point charge. Now these are the concentric spheres drawn, blue colored spheres are concentric spheres drawn around the positive charge. So each and every concentric sphere itself is a equipotential surfaces, because potential due to positive charge and some distance is given by 1 by 4 pi epsilon naught q by r. So let us consider we kept charge q at the center and consider the surface, the radius of the sphere is r. Then at this point, potential due to this positive charge at r distance, that is on the surface of the sphere, is 1 by 4 pi epsilon naught q by r. If you consider one more point here, it also indicated by the same formula, because from charge q, the distance is radius of the sphere r, hence the value of v is equal to 1 by 4 pi epsilon naught q by r. Similar to that, if we consider any point on the surface of the sphere of radius r, potential value is same. Hence on the surface potential is same. Hence the surface considered at some radius, the sphere considered at any radius itself becomes an equipotential surface. These are spherical equipotential surfaces drawn around a positive charge. Hence these are said to be spherical equipotential surfaces. Here let us see some properties of equipotential surfaces. Because if you consider this plane equipotential surfaces, potential is same at all points. Suppose we would like to move any charge along the surface, work done to move any charge along the surface is W is equal to Q into delta V. W is equal to Q into delta V. Delta V is the potential difference. Potential difference between any two points, as potential is constant, potential difference is 0 along the surface. Therefore, that value is equal to 0 because delta V is 0. Like this, even on spherical equipotential surfaces, suppose we would like to move any charge from here to here, the potential at these 2 points is same. First point and second point or any point on the surface possesses the same potential. Then here also work required to move any charge is equal to Q into delta V, that is equal to 0. So work done is 0. So important conclusion is work done to move a given charge along the equipotential surfaces must be 0 is the first thing. And one more thing, the electric field is normal to the equipotential surfaces. This is the direction of electric field E bar, which is making 90 degrees angle with equipotential surface. Here also the electric field lines are directed radially outward, and this is the equipotential surface here. The angle between the equipotential surface and the electric field direction is 90 degrees. Therefore, component of electric field is always perpendicular to the equipotential surface, or the component of electric field tangential to the equipotential surface is 0. Let us write some properties of equipotential surface here. So here these are the interesting points, some problems designed on the basis of this concept. As I explained so far, by using those pictures I explained that no work is done in moving a test charge from one point to another point on equipotential surface. So VB minus VA delta V is 0, hence work done is equal to 0 on any equipotential surfaces. So VB must be equal to VA, potential is same, hence work done is 0. That's what we concluded already. And the next point, the electric field is always perpendicular to the element dl of the equipotential surface. If we consider any small element, either plane equipotential or circular spherical equipotential surface, the electric field is always perpendicular to equipotential surface. Here, so that were already these 2 points were in previous concept, and electric field is always normal to the equipotential surface. Component of electric field tangential to the equipotential surface is 0. So next one, electrostatic potential energy. So next concept is regarding the energy. Suppose we have some charge Q1 at any point O. Let Q1 be a positive point size stationary charge. Let Q1 be a positive point size stationary charge at O. We would like to bring another charge from, let Q2 be any arbitrary charge, second charge, kept at infinity. It is slowly moving without any acceleration. It is slowly moving towards Q1 from infinity. Suppose at some arbitrary point P, now Q2 is at a distance R from Q1. Then work required to bring a Q2 charge from infinity to particular point P is equal to potential energy of the system of charges at R distance of separation. So only difference between potential and potential energy, potential is the work required to bring unit charge from infinite to particular point, whereas potential energy is the work required to bring the given charge from infinite to that point. So let us see the equation for potential energy. So work required to bring unit charge is V, then work required to bring Q amount of charge is QV, hence that is equal to potential energy of the system of charges. So electrostatic potential energy of two charges is given by, look into this animated diagram and explanation. Here in this coordinate system, XYZ coordinate system as they are shown in the diagram, let Q1 be any charge point positive charge kept at A, and B is another point positive charge kept at B. Then the radius vector or position vector of Q1 from O is R1 bar and position vector of B from O is R2 bar. Then the distance between the given two charges is R2 minus R1 bar in magnitude. So distance between them is magnitude of R2 bar minus R1 bar. Simply we represented, let it be by the value R21. Then work required to bring Q2 from infinite to this point is numerically equal to potential energy of the system of charges. numerically that is equal to, as we are bringing Q2 from infinity to that point, that is also equal to, this potential energy is also equal to work done in bringing the charge. Work done to bring the charge is, unit charge is V. Work done in bringing Q2 charge is Q2V. So for V formula is 1 by 4 pi epsilon naught Q1 by magnitude of R2 bar minus R1 bar V. Then Q2V is numerically equal to potential energy. Hence it is equal to 1 by 4 pi epsilon naught Q1 Q2 by distance between the charges. This is the magnitude of distance between the two charges. So potential energy is given by 1 by 4 pi epsilon naught Q1 Q2 by magnitude of R2 bar minus R1 bar. So remember that's the only difference for potential 1 by 4 pi epsilon naught Q1 by R, potential energy 1 by 4 pi epsilon naught Q1 Q2 by R. So Q2 into V is equal to work done in bringing the second charge, that is equal to potential energy. So simply, as we consider a magnitude of R2 bar minus R1 bar is equal to the R12 or R21, then 1 by 4 pi epsilon naught Q1 Q2 by R12 is the expression for potential energy of a pair of charges. So let us consider the expression for potential energy of group of charges. Potential energy of group of charges. Consider number of charges here. So let us look into same, consider coordinate system, xyz coordinate system. Consider number of charges here. Let Q1 is the charge kept at A and Q2 is the charge kept at B, as well as Q3 is the third charge kept at C. So the radius vector, respect to radius vector is Q1 at R1 bar, Q2 at R2 bar, as well as Q3 at R3 bar. Then distance between respect to charges. Let us look into the diagram and observe the distance between respect to charges. We consider the distance between A and B, that is Q1 and Q2 charges, is magnitude of R2 bar minus R1 bar. Similarly, distance between Q2 and Q3 is magnitude of R3 bar minus R2 bar. Distance between Q1 and Q3 is magnitude of R3 bar minus R1 bar. We know the three charges in the system, given system, and respect to distances between the pair of charges. Then potential energy of system. Potential energy is a scalar quantity. Potential energy due to the group of charges is simply equal to algebraic sum of potential energies between all pairs. Potential energy is a scalar quantity. Total potential energy of system is sum of potential energies of all pairs of the charges in the given group of system. Here totally there are three pairs. One pair is Q1 Q2, second pair is Q2 Q3, third pair is Q1 Q3. So if you find out potential energy for each pair that and add them, that becomes the potential energy of system of charges. Here for first pair Q1 Q2, it becomes 1 by 4 pi epsilon naught Q1 Q2 by magnitude of R2 bar minus R1 bar. So of course in numerical, while solving the problems, we know the value in centimeters or meters between charges, we use that value. In expression we are considered like this. So 1 by 4 pi epsilon naught Q1 Q2 by magnitude of R2 bar minus R1 bar. Between Q1 and Q3, 1 by 4 pi epsilon naught Q1 Q3 by magnitude of R3 bar minus R1 bar. As well as between Q1 and Q2, 1 by 4 pi epsilon naught Q2 Q3 by magnitude of R3 bar minus R2 bar. So this is the way in which we are adding potential energy of each pair of the given system. So addition of potential energy of each pair of given system gives the potential energy of the system. So this is a simply algebraic sum of addition of potential energy of each pair. So out of these charges, if any one is negative, suppose Q2, we assume Q2 is negative in this expression, for suppose. Then whenever Q2 comes, use negative sign. So here we have Q2, here expression is multiplied by minus 1. And there is no Q2, so it is as it is. In the third term, we have Q2, so multiply with minus 1. In this way, we get algebraic sum of potential energies, hence we get the expression for potential energy of system of charges. Here, so So if you consider simply magnet of R2 bar minus R1 bar is R12 and the next one is R31 and next one is R32, the simple expression is like this. 1 by 4 pi, if all are positive, the expression is in this form. 1 by 4 pi epsilon naught Q1 Q2 by R12 plus Q1 Q3 by R31 plus Q2 Q3 by R32. So electrostatic potential energy of n charges system, if there are n charges, we have to write like this: 1 by 4 pi epsilon naught, and we have to take the each pair, expression for each pair, and we have to consider all pairs. For each pair, write the potential energy formula and add them to get the potential energy. So this is the important. In recent years, when you look into any objective model exam, some problems were designed on this concept. Initially, charges are kept at vertices of a triangle. Charges are kept at vertices of a triangle, right angle triangle ABC. Here distance between A and B is R1 and A and C is R2 and B and C is R3, and three identical charges are kept at vertices of triangle. Okay. Then initial potential energy is known for us by using this similar formula: 1 by 4 pi epsilon naught Q1 Q2, of course Q square by R1, next Q square by R2 and Q square by R3. We find out this value of initial potential energy. We will find U1 for this system of charges. If the configuration changes to equilateral triangle, charges are remain same, but the triangle shape changes to equilateral triangle, each of side R, and Q1 Q2 Q's are same between the at the vertices, Q values are same at vertices. Then for the final configuration, it becomes U2, potential energy of the system is U2. Of course, this U2 is equal to, for the first pair, 1 by 4 pi epsilon naught Q square by R. For all pairs, we get the same expression. There are three such pairs into 3. This is U2. Then what is the work done in changing the shape of the triangle from first right angle triangle to second equilateral triangle is U2 minus U1. That is equal to U2 minus U1. Similarly, if it itself, initial itself is a equilateral triangle of side R, now it is increases to another equilateral triangle of side 2R, then what is the work done means here also we find out U1 for R distance of separation and U2 for 2R distance of separation equilateral triangle by using this similar expression. This is the main expression. The change in potential energy is equal to work done. The work done is equal to change in energy, especially here that energy changes in form of potential energy. So change in potential energy is equal to work done. We have good number of problems in objective by using this potential energy concept. So one more very important thing regarding potential is relations between field and potential. So here we know that E is the electric field, then V is the potential. The very first relation is E is equal to minus dV by dr. E is equal to, if V is in function of R, then electric field at any distance is calculated by the formula E is equal to minus dV by dr, or dV is equal to minus E bar dot dr bar. dV is equal to minus E bar dot dr bar. These formulas are applicable especially for uniform electric field. Electric field is uniform in a particular region. For uniform electric field, the relation between electric field and potential is given by knowing V, we find out E by the formula E is equal to minus dV by dr, or by knowing E, we find potential difference between 2 points by the formula dV is equal to minus E bar dot dr bar. Here one interesting conclusion, as we move, suppose this is the electric field, it shows the uniform electric field by the equally spaced parallel lines. If you move from point A to point B in the direction of electric field, potential goes on decreasing. VB is less than VA. As we are moving in the direction of electric field, potential goes on decreasing. If we move opposite, potential is increasing. Because work done increases when you move opposite, potential increases. As we are moving along the direction of electric field, potential decreases. This minus sign indicates that conclusion. dV is equal to minus E bar dot dr bar. In recent eamcet questions, here there is a triangle ABC. This triangle ABC is kept in uniform electric field. As this is the equilateral triangle, this angle is 60 and side of the triangle is some L. Then calculate the potential difference between A and B. That is the question. What is VA minus VB? A recent question. So VA minus VB, as it is in uniform electric field, this parallel line shows uniform electric field. Then potential difference between A and B is simply calculated by this formula, minus E bar dot dr bar. Of course, this is expansion EDR cos theta. So ER cos theta. So R is L here. E is given in the data, theta is 60 degrees. By substituting given E value and length of triangle and theta 60 degrees, we find out potential difference A and B. Of course, we get with negative sign. Like this, these are very much useful in solving objective questions. Good number of problems were designed on this concept. Whereas in case of variable electric field, if E is in function of R, due to point charge, if you consider any point charge and electric field due to point charge at some distance is 1 by 4 pi epsilon naught Q by R square. So then as R is increasing, E goes on decreasing, it is a variable electric field. In such case of variable electric fields, take integration on both sides. Then integral dV is equal to minus integral E bar dot dr bar. This is also very interesting, very important relation. Integral dV is equal to minus integral E bar dot dr bar. This is very much useful to find out potential due to charge distributed bodies. We have charge distributed bodies like hollow sphere and charge distributed body like solid sphere. Uniformly charge distributed solid sphere, uniformly charge distributed hollow spheres are there. In recent years, number of problems were given on this concept. A repeated question. To find out potential due to such hollow and solid spheres, we especially that is a variable electric field. To find out potential at any point, we definitely use this formula. Integral dV is equal to minus integral E bar dot dr bar. And next one, by knowing V, this is also given recent JEE main and eamcet exams. V is in function of x, y, z. It may be any value, a creative value. He may create potential in function of x, y, z in different ways. Then E bar is equal to minus dou V by dou x into I cap, minus dou V by dou y into z cap, minus dou V by dou z into k cap. Here simply when E is constant and minus dV by dr, when V is not constant, V is in function of x, y, z. Then V is a function of x, y, z. To find the electric field in that region by knowing V, then minus dou V by dou x into I cap, minus dou V by dou y into z cap, minus dou V by dou z into k cap. And similarly, just multiply this first equation on the board with Q on either side. QE, here this is QV. We know that QE is force, electrostatic force. QV is electrostatic potential energy. So here we have the relation between electrostatic force and potential energy. Similar to this first formula, E and V, we have F and U. F is equal to minus du by dr. And cross multiplying, we get change in potential energy equal to minus F bar dot dr bar. In case of variable electric fields, then the change in potential energy is calculated by the formula. Electric field is variable, force is also variable. Integral du is equal to minus integral F bar dot dr bar. By using these are the very important relations. In JEE main, in any competitive exam, plenty of problems were designed on these relations. So let us come to the potential due to charge distributed bodies. Now our discussion confined to potential. So far our discussion is mainly on potential due to point charge, potential due to multiple charges, potential energy between point charges, potential energy due to system of charges. This was the discussion. done so far. Now the discussion is about charge distributed, potential due to distributed charge. Here, let us consider a ring. This is the ring having radius r, and q amount of charge is distributed uniformly on the surface of the ring of radius r. We would like to find out potential due to this charged ring at some arbitrary point P. Let P be some arbitrary point. Potential due to this charged ring at some point P on the axis of the ring at a distance x from center of the ring. Here this is the very important, very simple derivation. First we calculate potential due to one point charge, then take algebraic sum, that means algebraic sum of all the charges, each and every charge is same distance. So from periphery of the ring, if you consider x is the distance of P from center and r is the radius, and this hypotenuse is square root of r square plus x square, each and every element is at same distance. So general formula 1 by 4 pi epsilon naught, let it be represented by k in the formula 1 by 4 pi epsilon naught, which is 9 into 10 power 9, is represented by k into q by distance of the P from charge, that is as he derived here, square root of x square plus r square. So as at x is equal to 0, denominator is least value and charge is kq by r, potential is kq by r. So at x is equal to 0, at this point potential energy is maximum, numerically kq by r. When you move either towards right side of the ring or left side of the ring, x goes on increasing, denominator increases and potential decreases. Hence the shape of the graph for potential on y-axis and distance from center of the ring on x-axis is as shown here. Next one, potential due to charged disk. While finding the disk, first we calculate the potential due to small element which is in form of a ring. First we consider this formula. A disk is combination of rings. So first we find out the potential due to small element of the disk in form of a ring, and by integrating we get the total potential. Hence the total potential is sigma by 2 epsilon naught into square root of r square plus x square minus x. Sigma is the surface charge density, that is q by pi r square. Then that is sigma by 2 epsilon naught into square root of r square plus x square minus x. This is the formula. Here also when x is 0, it has maximum potential, that is sigma r by 2 epsilon naught. Either x increasing towards right side or left side, the potential goes on decreasing. So this was about the potential due to ring along its axis and potential due to disk along this axis. So next one, potential due to charged ring, which is a sub-case of previous formula. So potential due to charged ring exactly at the center. In our previous part of our discussion, we calculated on the axis of the ring. Now at the center means x reduces to 0, hence it becomes V is equal to kq by r. Kq by r. Of course, charge is equal to, here V is equal to kq by r at the center of the ring, and k into q is equal to charge per unit length into length. Length is 2 pi r, length of the ring. By r get cancelled, and k into 2 pi lambda. K into 2 pi lambda is also equal to potential of the ring at the center. K 1 by 4 pi epsilon naught, lambda linear charge density, and 2 pi is constant. Then potential due to charged semicircular ring. So if you consider any part of the ring, full ring or semicircular ring, and any part of the ring as 1, 2, 3 diagrams. If you assume charge is q here, similarly this part of the ring also has the same charge, this part of the ring also has the same charge, then expression is same. Potential is algebraic sum of potential due to all elements. Hence in all these cases, providing q is the charge of the given element, q is same for a given element, then kq by r is the formula for all cases. So comes to next case, that is potential due to hollow sphere. Potential due to hollow sphere and solid sphere is the most very important cases in objective point of view. potential due to charged hollow sphere. So let us consider the hollow sphere as shown here. Let this be a hollow sphere for which charge is present only on the surface of the sphere. Charge is distributed uniformly only on the surface of the sphere. Like this, total amount of charge distributed is Q. R is the radius of the sphere. Then, first of all, at outside points, if you consider any point here, a small r that is greater than capital R, which is said to be outside point, and here potential is calculated by the formula V is equal to minus integral E bar dot dr bar. This is the formula. Already we derived this formula. We discussed this formula in the relation. And of course, E outside the sphere is known. E outside the sphere is 1 by 4 pi epsilon naught q by small r square. Replace E by 1 by 4 pi epsilon naught q by small r square, and by integrating it we get this formula. E is equal to 1 by 4 pi epsilon naught q by small r square. Here we have a hollow charged sphere having charge q and radius capital R. At outside point, which is at a distance small r, the electric field is given by 1 by 4 pi epsilon naught q by r square. By using this electric field in this formula, we get potential, that is 1 by 4 pi epsilon naught q by small r, q by small r. Of course, the charge is equal to surface charge density into area. Area of the sphere is equal to 4 pi r square. By replacing q in numerator by this formula, and we get sigma r square by epsilon naught r. Just to you remember the first expression for potential, you can transfer the formula modified to the second form, no problem. This is the important one. Next comes to the surface. When you comes to the surface, small r becomes capital R. Small r exactly distance of the point is equal to radius. So in this formula, replace small r by capital R, so that the potential on the surface of the sphere, hollow sphere, q by 4 pi epsilon naught into 1 by capital R. Next comes to inside. So here when it comes to inside, we know that E is equal to minus dV by dr. Comes to inside, we had this relation, E is equal to minus dV by dr. The known thing is, electric field inside the hollow sphere is 0. In electrostatic charge and field chapter, we know that electric field inside the charged hollow sphere is 0. Minus dV by dr means V is equal to constant, minus dV by dr 0. This implies potential is constant. Constant means that's value is same as the surface value. Therefore, inside the hollow charged sphere, potential is q by 4 pi epsilon naught into 1 by r. Here one interesting conclusion. Inside a hollow charged sphere, already we know electric field is 0, whereas potential is non-zero. Potential is non-zero and its value is 1 by 4 pi epsilon naught into q by r. So, here when you look into the recently given questions on this concept, generally either on the surface or at outside the surface, the potential due to the given sphere is proportional to 1 by r. So, V2 divided by V1 is equal to R1 divided by R2 is very much useful formula, which is obtained from this expression, first expression outside point, and it is very much useful to solve the recently given problems. So next case comes to potential due to charged non-conducting solid sphere. Suppose let us consider a solid sphere in which charge is distributed uniformly throughout the sphere. If you consider any atom, assume nucleus of the atom consisting of positive charges. If Z is the atomic number, Ze is the amount of positive charge inside the nucleus. That Ze is distributed uniformly inside the nucleus. Similar to nucleus of any atom. Here consider a uniformly charged distributed sphere having charge q and radius r. Okay. If you consider any point outside the charged sphere, For any outside point, the formula is same as the hollow sphere formula. Hence, outside point 1 by 4 pi epsilon naught q by r square is the electric field. 1 by 4 pi epsilon naught q by r is the potential. On the surface, small r becomes capital R. Hence, 1 by 4 pi epsilon naught q by r on the surface. So, outside point on the surface, these two expressions of potentials of solid sphere same as the hollow sphere formula. Next, come to the inside. Inside is an interesting one. Inside the hollow sphere and inside the solid sphere have different formulas of potential. Suppose let this one be the radius. Actually, this is the radius of the solid sphere, that is charge distributed sphere R, and this is the inside point. We assume one more point here. So I draw the line with some green color. See, the green color shows the inside point, and this is the Gaussian surface taken at inside point of the given solid charge distributed sphere, like this. Then at this point, what is the potential means? Work required to bring unit positive charge from infinite to surface of the sphere is V1. V1 is given by this formula 1 by 4 pi epsilon naught q by r V1. Work done up to surface. Work done to bring unit positive charge from infinite to the surface is V1. And V2 is the work done in bringing the unit positive charge from surface to the given point. This work in bringing unit charge is V2. Sum of V1 and V2 is the net potential at that point, and by adding those two values, ultimately this is the expression 1 by 4 pi epsilon naught into q by 2r cube. So I am rewriting the expression, that is 1 by 4 pi epsilon naught into q by 2r cube into 3 capital R square minus small r square. Undoubtedly, it is a typical formula, not easy to remember, but have to remember this equation. Especially in JEE Main, number of questions were given on this formula, which is difficult for any student to remember, but this is same formula is also useful as the gravitational potential in gravitation chapter. In gravitation chapter, we replace Q by Z, Q by M. Charge here we have charge, there we have mass Q by M, and 1 by 4 pi epsilon naught by Z. So Zm by 2r cube into 3r square minus r square is the gravitational potential. So here we are discussing electrostatic potential. 1 by 4 pi epsilon naught into Q divided by 2r cube into 3 capital R square minus small r square is the formula. At center of the sphere, when you comes to the center of the sphere, at center of the sphere small r is 0. Small r is 0. At center of the sphere, hence it becomes 1 by 4 pi epsilon naught into q by 2r cube into 3r square, that is q by r into 3 by 2. It is 3 by 2 times the value on surface. This is the surface value, this is the center value. Center value is 3 by 2 times value on the surface value. This is about the electrostatic potential. When you plot the graph from center to the surface, this is the expression. It goes on decreasing, hence this is the shape. It goes on decreasing. And from surface to beyond the surface, then above the surface of the earth inversely proportional to r, hence it is similar to rectangular hyperbola. And this is about the potential. Here one interesting problem. I completed the concepts of potential. Before concluding, this is one interesting problem because I selected this problem. These model problems, this is not a concept, this is one idea of the problem. These type of problems are very important in IIT and mains examinations. That's why I would like to explain this model problem. We have two concentric charged spheres, spherical shells. Here first one is of radius r1, this is radius r1 and charge q1. Second one, this is of radius r2 and the charge q2. Then question is, what is the potential on the surface of the first sphere? Second question is, what is the potential on the surface of the... So this is the first question. What is the potential on the surface of the inner sphere? What is the potential on the surface of the outer sphere? By knowing the explained concept and a little bit extra explanation, we can answer these questions. Suppose Q1 is the charge here. See, on the surface of the first sphere, we have charge Q1. Okay, these are spheres, hollow spheres, concentric spherical shells. It is surrounded by another charged spherical shell of charge Q2. Here we have to consider the induction phenomena. There are three methods of producing charges, charge produced by conduction or by friction or by induction. Here as there is no contact, there is no rubbing and there is no transformation, there is no friction, only phenomena is induction. So by the phenomena of induction, if Q1 is the charge on the outside surface of the inner spherical shell, observe my terminology, Q1 is the charge on outer surface of the inner spherical shell, then at the inner side of the outer spherical shell, at the inner surface of outer spherical shell, don't get confused, listen the concept carefully. At the inner surface of the outer spherical shell, a charge is induced in the phenomena of induction which is equal to minus Q1. Equal and opposite charge is induced here by the phenomena of induction, minus Q1. Minus Q1 is induced now. There is no such value in the given problem. We have to consider. And due to law of conservation of charge, charge is neither created nor destroyed. This is transferable. As minus Q1 is transferred here, the outer surface now possessing Q1 plus Q2 charge. This is the first step to answer this question. So this is the given problem and then this is the first step. Q1 is the charge on the outer surface, then induced charge at the inner surface of the outer shell is minus Q1. Due to law of conservation of charge, the charge on the outer spherical shell is Q1 plus Q2. Then now there are three charged spherical shells. Outer surface of the inner one, inner surface of outer one and outer surface of the outer one. Three charged spherical shells should be taken. Potential at any point is given by the algebraic sum of potential due to three spherical shells. So in that way we have to move forward to answer this question. Very important IIT examinations and JEE main examinations. Potential at point A due to first inner spherical shell, inner charged spherical shell, potential at A is already just discussed formula kq1 by r1. K refers to 1 by 4 pi epsilon naught on its surface. Next, due to minus q1 induced charge, this is point A is inside point. Point A is inside point due to the minus q1 charge. At inside point charge potential is constant, which is equal to surface value. Hence k into minus q1 by r2. Surface radius is r2. The value at any inside point is equal to surface value. So k into minus q1 divided by r2. Now as well as this A point is also inside point for q1 plus q2 spherical shell. This spherical shell is considered to be minus q1 spherical shell and q1 plus q2 spherical shell. Due to q1 plus q2 spherical shell, this is inside point. The potential at inside point is surface value. So k into q1 plus q2 by r2. This is the potential at A. Similarly, second question, potential at B. We have to take V1 due to inner sphere and V1 due to inside induced charged one and V due to outside charged one. Sum of these three potential is the potential at B. Due to inner charged spherical shell, this B is outside point which is at a distance r2 from its center. B is at a distance r2 from center of the q1 sphere. Hence the formula is here V is equal to, I am writing the expression for potential at B, that is equal to K into plus Q1 divided by R2 plus First step is completed. Second step, due to this one, the B is the surface of the charged spherical shell. Charge at the inner surface is minus Q1. So minus Q1 by R2. Due to Q1 plus Q2, it is the surface point. K into Q1 plus Q2 divided by R2. These two are not similar. These are different. In this way, we have to write the formula. Then potential difference. Sometimes he may ask the potential difference between A and B. Then we take VA minus VB. And this is the important discussion, students. In this part of our discussion, I explained the objective revision of the potential chapter. In this, I explained about the potential due to point charge, potential due to group of charges, equipotential surfaces, potential energy of the pair of charges, potential energy of system of charges, relation between potential and electric field, and potential energy due to charge distributed bodies. This is very important idea. I discussed the very essential and very required expressions of potential in objective examinations. This video is very much useful for your objective revision. Thank you for listening. Thank you very much.